लास्ट टाइम हमने टनलिंग प्रॉब्लम को देखा और उसके लिए हमने फाइंड द ट्रांसमिशन कोएफिशिएंट फॉर रेक्टेंगुलर बैरियर्स. Today we will use this quantum tunneling concept to understand another phenomenon called radioactivity. So I won't go into the details of the radioactivity, but let me construct the problem for you. So these heavy nuclei with the atomic mass above 80, they are found to be unstable, and the nuclei disintegrate into smaller nuclei, and the disintegration disintegration occurs in terms of decay of alpha particles, beta particles, and gamma rays. So
बोर्ड के साथ किया जाएगा.
we will talk about alpha decay. Alpha decay, that means the alpha particles are basically 2 protons and 2 neutrons, and we represent them like this. So we know helium has 2 protons, so we represent alpha particle as helium with a 2 positive charge, which means that you have only 2 protons, you don't have 2 electrons in it. So first we construct the phenomenology of the radioactive decay. The question is that if n represents the number of nuclei at time t, and p is the probability per unit time of decay. So then P times dt, that would be the probability so this is probability of decay in time interval d, and if dn, the number of nuclei which decay then we can relate these quantities like this. So the number of nuclei which would decay would be equal to the number of initial nuclei times the probability of decay in dt time, which is p dt. From here, if we rearrange the terms, dn over n equals to Okay, then we put a minus sign here because the final after dt the nuclei in your system has decreased. So this will account for the negative sign. This equals to minus dt. So let's integrate it over. Let's say if n0 are the number of nuclei at 0 time and np at certain other time, we integrate it over this limit and from 0 to 2. This will give me what? Log np minus log m0 that is equal to minus p, or I can quickly write this np over m0 equals to e power minus p. This is constant, so the number of nuclei, decayed nuclei would decrease with the exponentially decrease with the time. Let's define another quantity. Let's say that t naught is the time. So at t equals to t naught, the decayed nuclei are half of the initial nuclei. This is the time during which half of the nuclei in the system has decayed. If you put these conditions here, you will get 1/2 equals to e power minus p naught. Okay, so this will give me minus log 2 equals to minus naught and t naught equals to log 2 over 3, which is 0.69 over. This is what we call half-life. This half-life includes the probability of decay. So remember in our barrier problem, we calculated the transition coefficient, which is basically the probability of transmission of electron through the barrier. So this is the quantity we can construct using our barrier problem. So now let's say construct a model here. So let's say you have an alpha particle which has a charge of 2 electrons, positive 2 electrons, and the rest of the nucleus, which also has some positive charge on it. So when you bring these two systems closer to each other, what force they will feel? So you have a charged particle and another charged particle, both are positive. So what force between them? It's a Coulomb force. So it's a repulsive Coulomb force. So if you bring this alpha particle closer to the nuclei, it will feel stronger and stronger repulsion until it touches, let's say, two particles collide. And since nucleus is a stable system, which means that there must be some strong attractive force which can bind the two systems together. So let's say so here we are talking about bromine, which has atomic mass 12 and atomic number is 84. Okay. So here is your nucleus with two less and two neutron left. So polonium minus 4, this is weight is 208, and there is an alpha particle just touching this nucleus. So if this alpha particle moves away, then it feels the only attraction between the two systems is the Coulomb interaction. But if it moves inward, then the strong forces become dominant, and the system now becomes a system with 212 neutrons in it. If this is the center of alpha particle, this is the center of a nucleus, then if I construct a potential for the two.
So what is the strong force?
Let's assume that this is a strong force which is acting at a very short distance, which binds these positive charge together. So in the nucleus we have only positive charge, protons, and they have repulsive Coulomb force between them. But within the size of the nucleus, if this system is stable, then we have to assume some sort of strong force which overcomes that Coulomb repulsion. So let's see how this potential looks like. So let's draw let's take the origin or center of this P208 nucleus, and this is the radial distance R. And let's say this is the potential between alpha particle and the rest of the nucleus. So when it moves away from this position, then the only interaction between them is the Coulomb interaction. And what is that? If the charge of helium is what? 2 electrons. If V is the atomic number of the system, then the rest of the nucleus has a charge what? D minus 2. Right? We have taken 2 protons out of it. So the Coulomb interaction between them would be what? D minus 2 times the charge, then the charge of 2 protons, Coulomb constant K, and 1 over R. Right. So you have two systems, alpha particle and the rest of the nucleus. Alpha particle has charge positive 2 E because it's 2 protons. If Z is the atomic number of the whole system, then the charge on the rest of the nucleus would be D minus 2 times the electronic charge. Now you write the Coulomb potential. This is the charge of the proton, the alpha particle, charge of the rest of the nucleus times the Coulomb's constant divided by the R. So how this function looks like? So right at this point, if this alpha particle moves away, then it would experience 1 over R like potential. It should be what?
Negative.
Negative? Why?
Positive.
You have 2 protons in alpha particles. Yeah. This is positive. So if if E is the energy of emitted alpha particle, which would be the kinetic energy, then how the potential barrier would look like. So at this point, the height is this, width let's say this is R prime and this is R0. If this is the energy of the alpha particle, then the barrier is this. So your potential diffuses like 1 over R, and alpha particle has energy E alpha, which is the kinetic energy. Okay. So you just draw the straight line. So this is the energy of alpha particle. Okay. Now the barrier alpha particle would see is the potential energy above this E alpha. So this shaded area would be the barrier for the alpha particle. Now, in order to calculate the transmission coefficients, you need, well, first of all, remember, we calculated the transmission coefficient only for the rectangular barrier. This is not the rectangular barrier. Okay. So in the rectangular barrier, the expression we got was no. UPI, this is just to show that how you would construct the potential. This is the point at which alpha particle is just touching your rest of the nucleus. If you move this alpha particle inward, the strong forces would dominate and this becomes a one system. But if you move away from it, the potential it would feel is a Coulomb potential. So that's why we say that at this point onward, the potential between the two systems is 1 over R. E alpha is a constant because this is the emitted energy of alpha particle. So you are calculating, you are probing the alpha particle emitting from the nucleus. You know the energy. So these are the kinetic energies of the alpha particle. So for the rectangular barrier, we had expression like this. One plus d sine hyperbolic here, alpha, delta r is the width of the barrier, where d equals to u naught scale over 4e u naught minus e. So where e is the energy of the system, u naught is the height of the barrier. In this case, E alpha is the energy of the emitted alpha particle. So this is the energy. Okay, so we know that the alpha particle has that much energy. So initially, at this point, at t equals to 0, alpha particle is just at the outer surface of the nucleus. It has the energy E alpha. So with that energy, it has to cross this barrier. So now it becomes kind of a barrier problem we found last time. But this time, the barrier is not rectangular. E is the transmission coefficient. Okay. So what we need is to first calculate these. We need to calculate this width of the barrier delta r and this height. But if you can write the potential, if I put this R naught here, this will give me the potential energy at the distance R naught. So first of all, we need to find these distance R naught and R prime.
तो YP के लिए पूरी स्केल मैट्रिक्स
So if you look at the figure, R naught is the radius of the alpha particle plus the radius of the rest of the nucleus. Okay. If you know the radius of the nucleus, you can find by this expression. Where A is the atomic mass. If you know the atomic mass, you can get the radius of the nucleus. This is Fermi, so this F represents 10 power minus 15. So R naught is the sum of the radius of alpha particle and the radius of the rest of the nucleus. Now the R naught would be equal to 1.2 atomic mass of alpha is what? 4 plus atomic mass of rest of the nucleus is 208. And that equals to 9.01 per minute. So at this point, R naught, we can calculate the potential using this UR formula. So potential energy at R naught would be equal to D minus 2 D square A over R naught. You plug in the values of R naught from here, the charge of electron and the Coulomb's constant. And this turns out to be 26.21 million electron volts.
The radius of nucleus formula.
This is the empirical formula. This is a kind of a good estimate of nucleus when you scatter electrons from the nucleus. So from the scattering of electrons from the nuclei, you can get estimate for the radius. So this is empirical formula. This is like looking at the data, you can kind of write a formula which relates the radius with the atomic mass. So you get the potential, which is U naught at R naught. Next we want to find the R prime. So R equals to R prime, energy of the alpha particle and the potential energy equals, this is equals to the E alpha. Is this clear? E alpha is the energy of the alpha particle and UR is the potential energy at certain distance r. So we are talking about R prime. This is where the energy of the alpha particle and the potential energy. So it's the kinetic energy of the alpha particle and the potential energy of the particle become equal. So from here we know that the energy of the alpha particle that we get from the experiment, and this equals to 8.78 million electron volt. This is the quantity we get from experiment. So use the formula for the potential energy and put it equals to E alpha. This will give you minus 2 E square K over R prime equals to 8.78 million electrons. This will give you R prime equals to 26.9 femtometer. Millions. So these are the numbers we need. Now we can find the width of the barrier, which is the difference between R prime and R naught. We know the height of the barrier at R naught. So, how to approximate this potential? So we know the transmission coefficient for the rectangular barrier. This is not a rectangular barrier. Can we represent? Can we use our transmission coefficient which we got from rectangular barrier and use it for this potential? Right. Okay. 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 So that's a good approximation. So what he's saying is that if you have a function going like this, one way to replace this function with a small rectangle like these, where the center of these rectangles lie on the actual curve. So in this way, we know that we know the transmission coefficient for a rectangular barrier. So we have the multiple rectangular barriers attached to each other. So let's try this approximation. special function, and the barrier is R naught. So let's divide this R delta R into equal, let's say, into 5 segments of equal width. Where the midpoint represents the potential energy at, so this is my R1, R2, R3, R4, and the midpoint is just the average of R naught and R1. At this point, I plug this point in the potential. This will give me U1. Similarly, from here, I get U2. So in this way, all of these rectangles, you know the width of these rectangles and the heights of these rectangles. Sorry? No. I'm representing this 1 over R function by putting these rectangles next to each other. Now R naught, the potential at R naught is this one, but I'm representing it with a rectangular barrier. So the height of the barrier would be the position, the potential energy at this point. So you get this, so find this point, plug it in the formula, you will get the height of the barrier. So if you integrate it, what we will get is area under the curve, and that represents what? No, the thing is, we are not calculating the area here. What we want is that we want the transmission coefficient. But the problem is that the transmission coefficient, this we obtained it for a rectangular barrier, not for this barrier. So we replace this barrier with these rectangles. So if I know this width and the height of this barrier, I can find the transmission coefficient for this barrier. Let's say this is T1, this is T2. Fine. Okay. So the total transmission coefficient would be what? Of course, सारे के रेक्टेंगल्स में इनके बिग पॉइंट्स पे आपने बिग पॉइंट्स पे जो हाइट है वो कैलकुलेट करेंगे फ्रॉम दिस फॉर्मूला. So if T1, T2, T3, T4 and T5 are the transmission coefficients for these 5 barriers, what would be the total transmission coefficient? Sorry? Sum of all these small t's. Anybody else? Integral of what? But that's a constant. So one is okay. Who would say that it's the sum of all these coefficients? Raise your hand. Is this the sum of all these small t's? 4 average? Okay, anybody else? Look, let's look at it from another angle. Let's say you have a barrier like this. Okay, and your wave is traveling from this point. So part of this would appear here, and part of this would appear here. So okay, so this is your actual flux. A part of that flux will cross this barrier, and then part of this flux will cross this barrier. Is this the sum of all three? No, it's not the sum of all three. Is it? It's the product. This is the transmission probability from this times the transmission probability from this barrier times the transmission probability from this barrier. So your T total T would be T1 times T2 T4 times T6.
बड़े रेक्टेंगल के बेसिकली से वो जो ट्रायंगल है उसका बड़े रेक्टेंगल का रिलेटेड वो ट्रांसमिशन कोएफिशिएंट से भाग करके
जैसे अगर हम सिर्फ डेल्टा आर विड्थ ले और डेल्टा यू जो है हाइट ले
रेक्टेंगल का निकाल के हाफ कर देंगे तो ऑलमोस्ट सभी अप्रोक्सीमेट
ओके, लेकिन वाई टेक हाफ आप का जो एक्सप्रेशन है उसमें देखेंगे ये अल्फा डेल्टा आर आ रहा है. दैट्स द एरिया ऑफ है ना. इट्स नॉट रियली एन एरिया बट जो आपका जो हाइट है वो अल्फा के अंदर आ रही है और डेल्टा आर इज अ विड्थ. सो इट्स अ वेरी कॉम्प्लिकेटेड रिलेशन बिटवीन द हाइट्स एंड द विड्थ. इट्स नॉट लाइक स्ट्रेट फॉरवर्ड प्रोडक्ट. Right. Okay. Right. So this is why I said कि अगर आप इनको थोड़ा सा इनके दरमियान स्पेस इंट्रोड्यूस कर दें तो क्या होगा कि यहाँ से जो वेव आई है इसका पार्ट जो है इट विल अपीयर हियर. So a part of that would be reflected back and some small part will be transmitted. So that's why I said कि जो फ्लक्स पहले बैरियर में से पास करेगा उसका फ्रैक्शन जो है दूसरे बैरियर से पास करेगा. So that's why it should be a product, not the sum. So this is your flux, a part of it transmits, and then part of this will transmit again. So इसका जो total जो आपके पास flux यहाँ पे appear होगा, that's the product of transmission coefficient of this times this. Right. No, this is just to tell you that why it is a product. लेकिन अगर मैं इसको ज्वाइन कर दूँ यहाँ पे, तो यहाँ पे ये प्रॉब्लम इस सारी जो हमारे मेथोडोलॉजी इसमें प्रॉब्लम ये होगी कि अगर मैं इसको इस तरीके से रिप्रेजेंट करता हूँ तो देन यू कैन करेक्टली आर्गू कि यहाँ से भी कुछ फ्लक्स इस बाउंड्री से क्रॉस होना चाहिए. So this does not represent the actual transmission coefficient from this battery. So ये एक approximate value है. But since जो हमारे पास फॉर्मूला है वो सिर्फ रेक्टेंगुलर बैरियर के लिए, so if we are okay with the error we're going to get, then we can use this kind of methodology. But you will see that the final number you will get is pretty close to the actual number. So आपके पास 5 barriers हैं, उनकी width given है, उनकी height given है. So there, using this formula, you can get the T1s from there. If you take the product of all three, the value you get is this number. This is the transmission coefficient. This is the probability of crossing that barrier. What we need is the probability per unit time of decay, or the probability per unit time of transmission. Now you calculate this T1 from this barrier, T2 from there. You use this formula. So calculate for each individual value and then just take the product. Okay, to calculate the probability per unit time, we know the E alpha. E alpha is this is the kinetic energy of alpha particle. So let's say that before it emits inside the nucleus, it has that kinetic energy and it is bouncing off from this potential valve. So before it emits, it is residing in this potential valve. So it is residing less than R, region less than R naught. It emits with the kinetic energy E alpha. Let's assume that the alpha particle is bouncing off from the wall of this potential valve. This is inside the nucleus. So, if this is the kinetic energy, you can calculate the velocity of this alpha particle, which is mv square, half mv square. From there you get the velocity, and the velocity turns out to be 2.06 times 10 power 7 meter per second. So, the frequency with which it hits this wall would be what? If this is the velocity, and that total distance is 2r naught, then the frequency would be V over 2r naught okay. So let's say this is a classical particle and it is moving in between these two walls. The width of is 2r naught. If v is the velocity, then this is, what does it mean? Velocity is distance is covered in unit time. So the distance it covers for so the time to cover this much distance to R naught is what? Pi by if you know the angular velocity. So this is 1.14 times 10 power 21 second inverse. So let's say it is like oscillating in between the balls. No, it's not getting a kinetic energy by hitting the ball. We are assuming that inside the nucleus it has a kinetic energy electron, and with that energy it is like oscillating between the two walls. So the frequency with which it hits this wall would be just velocity over the width of the wall inside the vessel. Okay, so the probability of emission per unit time depends upon the probability amplitude times the frequency with which it is hitting that wall. And that probability turns out to be 4.54 times 10 power minus 8 second inverse. So let's say you have a classical particle bound between the two walls, and the width of the region is 2r0. You know the velocity. You want to find the frequency or the number of times it hits the wall in 1 second. So velocity is what? Distance over time, and I divide it with the total distance available. This will give me a number per unit time. That will be the frequency. Once we know the probability, we can calculate the half-life. So T naught calculated from this model will be divided by T, and that would turn out to be we need T is the probability of emission, right? F is the frequency or the number of times it's hitting that wall in unit time. Okay. So the probability per unit time would be this frequency times the probability. T is the transmission coefficient. जो हमने यहाँ पे calculate. So T is the emission probability. Per unit time, you multiply it with the frequency with which it is hitting that wall. So in this case, this would be .25 10 per minus 6 seconds. and the experimental value is 0.3 sine 10 to the minus 6. So you can see that the right. This divided by p. No, I think I made a mistake. This is sorry. This is plus 6. Okay, so let's recall everything what we have done. So the problem was that the potential barrier for alpha particle was not a rectangular barrier. Okay. So we approximate it with the small rectangular barriers attached to it. Okay. So that we can calculate the transmission coefficient from each small barrier. So the total barrier, so the total transmission coefficient would be the product of all the transmission coefficients from the small barriers. So this was the key point. To calculate these parameters for the barriers, we just use we know that the interaction potential between the two objects is the Coulomb potential. We expected the smallest R naught by looking at the radii of the alpha particles and the rest of the nucleus. And the barrier width we get by putting this potential energy of the alpha particle equals to its kinetic energy. From there we get the width of the barrier. Once we know the width of the barrier and the height, then we use that approximation. We approximated this 1 over r function by joining these small rectangles to each other. And that's how we get the probability per unit time to pass through this barrier. From there we get the half-life. And the half-life we can relate with the experimental value. So now question about overall methodology. T naught is the half-life of that system. No, T naught is the half-life is what? Half-life is the time during which half of your initial nuclei will decay. That's what we approximately say. Okay, that's a good question. Inside, we don't know what's the energy of the alpha particle inside the nucleus. But it is emitting with the that kinetic energy. So, we assume that inside the nucleus, before it emits, it becomes a free particle. So this is again our assumption that inside the nucleus, before emission, it becomes a free particle which is bouncing off that potential level with this kinetic energy. Sorry? Outside the nucleus, because it has a barrier, right? Its energy is less than the height of the barrier, so it has to overcome this one. So this is practically forbidden. So that's why we use our transmission coefficient from the quantum mechanical theory. Any other question? So the problems you may get would be like this. You will be given the potential, the parameters for the potential value, like the width and the height of it. And then you have to calculate the transmission coefficient from the formula. And then manipulate that transmission coefficient meaningfully to get the right answer. In the next lecture, we will look at another very interesting application of tunneling problem, which is the scanning from the microscope. And then we will practice two problems